Hey everybody, welcome to this episode of Kapow Science. Like all episodes, we're going to try to walk through this in detail, perhaps more detail than you need. I invite you to use the scrubber bar to skip ahead to the part that you want to find. Closed captions are always welcome, and you're also welcome to use variable speed playback to make this move faster or slower to help you understand and also maintain your attention span. So I won't be offended if you use any of those functions. Please do so as appropriate. Good luck. Hello friends, Mr. Brocklehurst here. I'm going to walk us through at least the beginning part of the wheel and axle gizmos lab, and then kind of give us some tips on the remaining parts as well that are due for before you come back to the next Zoom meeting for science. Okay, so let's get started. Right away, there's some instructions. We want to make sure that we're following the instructions as all the way through. There's no point in us writing instructions that we don't want followed. We want them all followed. Respond to all the questions and prompts in the orange boxes. So as you look through this, you'll see that there are orange boxes that have a white background to it. That means you need to respond in those. Okay. Vocabulary needed during this particular activity is effort, force, load, mechanical advantage, radius, wheel, and axle. And for the most part, all of these have been used, whether we're referring to levers or inclined planes. We've talked about effort, we've talked about force and load, we've talked about mechanical advantage. What might be new to us is this word radius. Radius refers to the distance from the center of a circle to the outside part of the circle, what we call the circumference. So from the center to the outermost part of the circle, that distance, that is the radius. Okay, and we'll talk about wheel and axle as we go through it. Okay, so the first part for this is to just kind of do some intro and some warm-up. Let's get started on question number one. A ship captain uses a steering wheel, also called a helm, to turn the rudder of a sailing ship. Do you think it would be easier for him to turn a large wheel or a small wheel? Explain why you think so. And so we're asking you to form a hypothesis here. You're going to complete the sentence. It will be easier for him to turn a large wheel or a small wheel, and then give us a reason for that. Go ahead and do that. Pause the video here if you need to and complete question number one. I'll wait. Okay, let's keep going. Let's move on to number two. Which screwdriver do you think would turn the screw most easily? Now we have two choices here. We've got this screwdriver and this screwdriver, and the only difference is the thickness of the handle of that. Do you think it's going to be easier to turn a thin-handled screwdriver or a thick handle? In order to do that, we're asking you to double-click on this or single-click and use the edit tool, and then you can kind of take this oval and move it over to whichever one you want to use for your answer. Okay, so please do that next, and then answer the following question. I chose this screwdriver because. Give us a reason why you chose either the thin handle or the thick handle. I'll pause the video here, or I recommend that you pause the video here while we wait for you to complete that, and then we'll move forward. Okay, let's go move down to the warm-up now. The wheel and axle gizmo shows a simple machine called a wheel and axle. In this machine, the outer wheel and there's also an inner axle. This is used to pull a load of rocks. Let's take a look at it. And in a moment, we're going to add an athlete to the thing and see if they're strong enough to move the wheel for question number one. Okay, so I'm going to ask you to click on this. Let's open up the gizmo. And I'm not sure if you're going to have to log in or enroll in your teacher's class, but you can make sure that happens. I'm going to log in using my password stuff. And you know, you're probably enrolled in one of your teacher's classes, so make sure that you're accessing it through that. I'm going to go to the wheel and axle, and I'm going to launch the gizmo. Okay, once I'm in here, you can see here's the wheel. The red part is the axle. I'm going to drag an athlete over to the wheel, and the athlete is going to see if they're strong enough. At this point, I hit the play button, I see the time is moving forward, and nothing is happening or nothing's moving. So this athlete is not strong enough to pull this pile of rocks. I'm going to hit the pause. I'm going to add another athlete. She looks pretty strong. Let's do that and hit the play button again. So even two of them are not strong enough. I can tell it's going because the time is elapsing there. I'm going to add a third athlete here and see if the combination of all three of now suddenly all three of them are strong enough to drag this pile of rocks along. Okay, so 1 and 2 were not enough, but the third one finally got it moving. You can see that there. Okay, I'm going to come back to my notes for a moment. And so in this first part, drag an athlete to the wheel and press play. The athlete pushes the wheel with a certain amount of force. Is the athlete strong enough to move the wheel? And I'm going to type it, no, they are not. I click reset, I drag more athletes to the wheel. The total force the athletes exert on the wheel is called the effort. How many athletes does it take to move the load of rocks? Do you recall how many athletes it took? This time it took 3 athletes. Okay, and I believe that the simulation is set up so that all the athletes are of equal strength, not one is stronger than the other. They count as single units of effort for the most part. Okay, are there any questions that you have about the wheel and axle warm-up at this point in time? You should contact your teacher either through the Zoom or through an email and ask them at this point. Our next part of this assignment is to do activity A, which is meant to be done independently by students. What's important is that you have the gizmo ready to go. Here's the gizmo once again, and that you hit reset before you start an activity, because that sets all the defaults regularly, and that way we're making sure that you have an experience that is the way we plan it to go, that you don't have settings that are way off and you have a really weird data that comes out of it. Okay, so similar to most labs that we do, we have some observation. The radius is what we want you to observe in this first part. So that's the distance from the center of the wheel to the edge of the wheel, essentially. So this is the distance from this red part out to essentially where the athlete is going to walk here. That's the distance the radius is referring to. I didn't hit the reset button yet, but I can in a moment. I just wanted the athlete to be there because that's really the distance that we want. Okay. All right. That's referring to the radius. Okay. Once again, all athletes exert the same amount of force. Even though some might look stronger than others, they all are exerting the same amount of force. All right, so at this point, we'd like you to kind of come up with your own hypothesis. If the wheel radius is increased, if you change the wheel radius and you make it bigger, do you need more effort to turn the wheel? Or we're measuring effort by the number of athletes. So if you increase the wheel radius like so, is that going to require more athletes, or will it require fewer athletes to turn the wheel, or does it have no impact at all? So at this point, I'd like you to complete this if you think the effort needed to turn the wheel will either increase or decrease or stay the same here, and then give us a reason for your response. You can pause the video here before you continue. Unpause it when you're ready to move on. Okay, our next task is to collect the data, and we're basically going to complete this table, or the right-hand column of the table as we go on. So I need a wheel radius of 6 and an axle radius of 4, and I'm looking for the smallest number of athletes needed. So I'm going to set my wheel radius to 6, my axle radius to 4, and I'm just going to give it a try at 3 and just see what happens. 3 athletes is not enough to get this moving. So I'm going to hit the reset. I'm going to add another athlete. 4 athletes, not enough to get this going. Add another athlete. 5 athletes, still not enough to get this moving. Let's go 6 athletes. 6 athletes, still not enough to get this moving. Add a 7th athlete. 7th athlete, ooh, this is not working out well. Let's cross our fingers here. 8 athletes now. 8 athletes seems to be the smallest number. Now, if I had a 9th athlete to add, obviously a 9th person is going to be able to make it turn 2, but we want the smallest number. So even if there was a 9th person I could add, I would want the smallest number. I would use 8 as my answer for this one. So I'm going to type in an 8 here. And I'm going to invite you to next reset your wheel radius at 8 and try it again. See if 8 is still needed to move the wheel, or if you can get away with even less athletes. And then you're going to do so for 10 and 12 meter radius as well for the wheel, keeping the axle radius the same. Remember, we want to change one independent variable at a time, not multiple variables. Okay, we want to know what caused it. Okay, so pause the video here and complete your table. Okay, welcome back. At this point, you should have completed the entire right-hand column of the table, and a pattern should have emerged. You should see that as the wheel radius is increased, either the amount of effort required also increased or decreased or stayed the same. A pattern should be clear to you now. At this point, you're going to want to complete the sentence following below in number 4. As the wheel radius increased, the effort needed increased, decreased, or stayed the same. You should be able to describe that pattern here. Do that now. Okay, welcome back. On question number 5, you should now be able to answer the question like, how is a wheel and axle useful? So a wheel and axle are useful in order to either increase the effort or decrease the effort required to turn an axle. Now, the other thing that you might make note of is the distance that the athlete walked. I don't think it's necessary to answer question number 5. You should be able to answer it based on the pattern you've seen in your data. A wheel and axle are useful to increase the effort needed or decrease the effort needed. What is that? The answer to that at this point. Put that into question number 5, and then we'll move forward. Okay, welcome back. At this point, we're going to talk about activity B. Once again, this is still considered independent work, but I'm going to try to walk you through some of this. Similar to part A, we're going to adjust a variable. In this case, we are not adjusting the wheel radius. We're going to adjust the axle radius. The axle radius is different from the wheel radius. The axle radius, once again, that is the size of the red part there. Okay, so how big is that going to be, and how will that affect the amount of effort needed? So I'm going to ask you to pause the video here, fill out your hypothesis. If the axle radius is decreased, then the effort needed to turn the wheel will increase, decrease, or stay the same. Give us a reason for that. Pause the video here, complete the hypothesis, and then unpause to continue. Okay, now that you've created the first part of your hypothesis, we're going to move on to number 3, collect data, which also includes a little bit of hypothesizing as well. So we are going to adjust the wheel radius to 12, and at this point we're going to hold that constant for all 4 trials. We will adjust the axle radius for each trial. We're going to start with an 8-meter axle radius, then 6, then 4, then 2. So I'm going to set it up, but I'm not going to play it for the first one. So I want a wheel radius of 12. Almost, and an axle radius of 8. Okay, so that's what it looks like. And we are predicting what is the minimum amount of athletes needed. Now, if I hit play here, it may move. We'll find out in a moment. But I'm going to ask you to make your predictions somewhere between 1 and 8, or sorry, 0 and 8 athletes, because that's really the only thing that the simulation can set up. So predict your number of athletes needed for between 0 and 8. How many athletes are going to be needed? You want the smallest number needed to turn the wheel. And then I'm going to ask you to make those predictions for 12 and 6, 12 and 4, and 12 and 2 wheel to axle radii, respectively. Pause the video here. Make your predictions. Be honest with yourself. Be honest with the scientific process. Make sure your predictions are predictions, not postdictions, right? We want to get better at making predictions. And the only way we're going to get better at that is by practice. So once again, pause the video, make your predictions, and then we can test the actual number of athletes needed. Remember, you're going for the smallest number needed. Okay. Okay, now that we've finished our predictions here, you should have filled out this first column. We're going to actually run the simulation for 12 and 8 and test our hypothesis here. Now, the first thing I'm going to do is I'm going to test it out at the 12 and 8. And so I'll run the simulation, and it's important that we run it all the way to the end. Okay, and the reason it's important that we run it all the way to the end is I can see that 8 athletes was enough to move the pile of rocks, but in addition to that, I also need to get this number, 37.5 meters. Okay, and the reason I need that number is I'm going to put this in here. I'm going to put 8 and 37.5 meters. And the reason I need that, and before I continue, I want to make sure that I actually needed 8. So I need to go back, I need to test it at 7. Is 7 athletes, I'm going to take one of these athletes away, is that enough to actually move that? Because I wanted the smallest number, remember. So I'll try it again and I find out 7 athletes, not enough. You can see the time moving forward, but nothing's happening here on the wheel. So 8 seems to be the smallest number I can use and actually get away with that. You're going to try the same thing for 12 and 6. Figure out the actual number of athletes you need, the smallest number of athletes that you can use to get it moving, and then the distance that they walked. Okay, so you're measuring 2 things, 2 dependent variables here, while we're changing 1 independent variable. Pause the video here and move forward with your data collection. Unpause when you're ready. Okay friends, we're going to finish today by moving along with our analysis and our extension. So at this point you should have a clear pattern for both the number of athletes needed, which represents the amount of effort, but also the distance walked. And you should be able to make 2 conclusions based on those 2 patterns. So as the axle radius decreased, did the effort increase, decrease, or stay the same? Remember, we're measuring effort by the number of athletes that you need. And then also, did the distance the athletes walk, did that increase, decrease, or stay the same as the axle radius decreased? Okay. Once you get done with that, we're going to move down to number 5. The wheel and axle is helpful because it reduces the effort needed to move a load. If it reduces the effort, what do you trade for that? I mean, obviously we want things to be easier, but that comes at a cost. So what is the disadvantage to actually reducing that effort? What else changed and how did it change? So you're going to have to look back at your data to be able to answer number 5. Once you do that, put that in words here. A complete sentence would be great. And then when you're done with that, you can move on to turning in this document in Canvas. This is something we've done many times with Google LTI or Google assignments in Canvas. I trust that you'll be able to figure that out. If not, contact your teacher at any point through the Zoom session or on email to answer these questions. Okay, good luck. I look forward to seeing you in our next class. Bye-bye.